Good morning and welcome to MAE 106, Discrete Mathematics with Probability. My name is Richard Kohar and this is Lecture 5, Logical Equivalence and Derived Logical Implications. And I hope everyone can hear the audio okay. If so, give a thumbs up in the chat. Hopefully the connection is running well this morning. Just checks. Yep, perfect. Thank you. Okay, so this morning we're going to talk about, well, again, logical equivalence and derived logical implications. The first thing that we're going to talk about is the biconditional. Perfect. Good to see everyone this morning. Here's the biconditional. So this is kind of another logical connector, or if you'd like. So this is P, and then this is a back and forth arrow, and I have Q. And what this denotes is the proposition P if and only if Q. So you could think of, let's say, here's an example. Say like the tea kettle is boiling, or sorry, is whistling. And this is where we use that turn of phrase. If and only if the water is boiling. Okay. So with the biconditional, it's that P and Q must have the same truth value for it to be true. So the truth table looks something like this. If I have P, I have Q, and here's P, back and forth. There we go. And good morning. Okay, I was just looking up at the chat. Good. Okay, so again, it must have the same truth value to be true. So in this case, this is the same truth value, true and true, so this is true. This is the one where it's got the same truth value, so that's false and false, so that makes this true. And these cases are where they don't match. So again, P, Q, have the same truth value. For to be true. Okay. So why are we using this back and forth arrow? It's so that you can actually think of it as going in the first direction and in the reverse direction. So what that means is that if I'm thinking about this, they can think of it as P implies Q, and going in the reverse direction, so from Q to P, so Q implies P. Okay, so let's do a truth table for each of these. Since we spent so much time yesterday, we might as well put our skills to use. So I have P, Q, P if and only if Q. Then I'll have P implies Q, Q implies P, and then putting it together, I have the P implies Q, and Q implies P. So, again, we can just write out our usual enumeration of all the possibilities for assigning true and false to the first, for the prime propositions. Then we have just, we'll copy it down from our biconditional, which is that P and Q must have the same truth value for it to be true. Then, using our implication, again, if I stepped in poison ivy, I get a rash, this is true. I stepped in poison ivy, I didn't get a rash, this is not true. Stepped in poison ivy and I didn't step in poison ivy, I got a rash, this is possible, and I didn't step in it, I didn't get a rash. So that's true. In this case, Q implies P. Now I'm going from this column to this column. So I stepped in poison ivy, I didn't get a rash, I stepped in poison ivy, I got a rash, so this is true. I didn't step in poison ivy, but I got a rash, this is true. I stepped in poison ivy, but I didn't get one, this is false. And I stepped in poison ivy, and I didn't step in poison ivy, and I didn't get a rash, and this is true. Okay. And now I have to do the AND operation on it. So I'm using this column and this column. So true and true, this is true, true. For the AND, it needs to be both true. And lastly here. So what we notice is that this column here just kind of and here. So these have the same truth table. And these are what we call logically equivalent. Okay. So, what does that mean? We'll just write this out a little bit in a better definition. So here's the second page. So two propositions logically equivalent if they have the same truth table. Okay, and we denote this using so it's denoted by this double back and forth arrow. So going back to here, what I can then say is that P, if and only if Q is logically equivalent to P implies Q and Q implies P. So I'll just write that. So from before, P, if and only if Q is logically equivalent to P implies Q and Q implies P. Okay, so let's do an example. So this could be like a question. So show that P implies Q is logically equivalent to not P or Q. So to show this logical equivalence, we have to do our truth table. So we have P, we have Q, P implies Q, and then we'll do the not P or Q. Okay, so I want you to take about a minute and just fill in that table. And so while you do that, I'm going to write it out. I'm going to hide it just a little bit below here. Okay, so hopefully you were able to complete that table. What we have then is we have PQ, P implies Q. Okay, so this is just our implication right here. So again, true, false, true, true. With the not P, this just flips this column, so it becomes false, false, true, true. And then I'm using this column and this column to do the OR. So false or true, so that's true. false or false, that's false. True or true, this is true, and true or false, this is true. So since these are the same truth table. Oh yeah, I should make this symbol with the 3 dots. The inverted is this is called since. And right here is therefore. So therefore, P implies Q is logically equivalent to not P or Q. So is everyone okay with that? And that's the end of that example, so I'll just usually I put some sort of symbol. Okay, so far so good. So then, we can do another example. So let's do is not P implies Q logically equivalent to P and not Q? Okay. Finally got my chat working. Excellent. And again, if there's something that goes wrong, I usually have my email open. Let me just check, and I don't see any emails, so that's good. So again, we'll construct a truth table. So I'm just looking on the left-hand side. I'm going to construct the truth table for this proposition here, and then I construct as well for this. So I was working on the inside of the brackets, and then I'm going to take the negation of it, and that would be the complete table for the left-hand side. And then on the right-hand side, I'm going to need not Q, and then I'll use the not Q and the P and join that together with the and. All right. Okay, so there's the implication, and now I'm just going to flip it, so I get false, true, false, false. Did I do? Yep. And then I take this column and flip it, so it becomes false, true, false, true. And lastly, I'll take this column and this column and do the and. So again, it has to be the same. It has to be both true to be true, otherwise it's false. So this is false, this is true, this is false, and this is false. Okay, so then we look at here. I'm going to look at here. And no, it's not. So these are not the same truth tables. Therefore, not logically equivalent. Oh, I am looking at the wrong. Good catch. So where did I put the correction tape though? Right here. So that was a test. Okay, so now that I'm looking at the correct one, can we appreciate how satisfying my handwriting is? I guess you can appreciate it. So it's probably another reason why I usually put some boxes down. There we go. So false, true, false, false. So yes, those are the same truth tables. So therefore it's logically equivalent. Or in other words, we'll do not P implies Q, logically equivalent to P and not Q. Okay, and that's the end of that. So thank you for keeping an eye on that. Okay. So the next thing that we have is called derived logical implications. Okay, so say we have a given implication, we have P implies Q, so there's kind of the original implication. There are three associated or derived implications that we can come from this. So The first one is called the contrapositive. And the contrapositive is by negating Q, which implies not P. This is called the contrapositive. And I'll just kind of switch into a different. So if I stepped in poison ivy, then I get a rash. This one says then, so negating that, so here's my Q and here's my P. If I don't have a rash, then I didn't step in poison ivy. Okay, so that's the contrapositive. The next one that I can is we can do the converse. And so that's if I had P implies Q, the converse would be Q implies P. And it's not like the shoes. It's, you'll hear this in English. So like if I stepped in poison ivy, then I got a rash. And sometimes you'll hear, and conversely, then they mean that they're going to start to go in the reverse direction of the implication. So the converse of this would be if I get a rash, then I stepped in poison ivy. Hopefully my pen doesn't die out for the last example. I have one more. So there's the third. And this one is called the inverse. So I have not P implies not Q. And so with that one, it's the inverse. And I wonder if this pen will hold out. So again, I negate the P. So if I didn't step in poison ivy, then I didn't get a rash. Okay. So what I can tell you is, let's go with 4. What I can say is that the implication P implies Q. I can tell you that this is logically equivalent to the contrapositive. Okay. But the implication is not equivalent to the converse or the inverse. So it's not to the converse. And it's not logically equivalent to the inverse. But what I can tell you is that the converse and the inverse are logically equivalent. So the implication and the contrapositive are logically equivalent. And same thing with the converse and the inverse. Okay. So what does this mean? This means that for me to say, just using our rule right here, for me to say if I stepped in poison ivy then I got a rash, then an equivalent way for me to say is that if I don't have a rash, then I didn't step in poison ivy. And also this means that if I looked at the converse, which is if I got a rash then I stepped in poison ivy, then the logical equivalence is if I didn't step in poison ivy, then I didn't get a rash. Okay. So you might not believe it thinking about it in terms of kind of as a... Sometimes it's difficult to think about it in terms of the situation, and that's why we resort to using logic. So we can think about it and work it out, and if we can show that this proposition is got the same truth table as this proposition, then they're logically equivalent. And same thing, if I look at the truth table for this one and I look at the truth table for this one and they're not the same, well then they're not logically equivalent. So what we can do with the remaining time is we can do truth tables for those and prove So some people start to get worried about proofs, but this is really what we're doing is a proof. So let's be adults, call it what it is. It's a proof. So we'll just create these tables. So again, we just write out our implication truth table for this. We flipped the values for Q. And again, flip the values for P. Doing the implication. And making sure that I'm looking at the right columns. Right? I want to make sure that I'm looking at this one. And it's okay to make mistakes. It's just I don't want to make the same mistakes twice. Making the same mistake twice is boring. That's the sad part about getting old. You end up making the same mistakes over again. You never get to make new ones and be excited or surprised anymore. So we have the same truth values. So this is the same truth table. So therefore, they are logically equivalent. Or in other words, what we've shown is that that's in symbolic. So we can do the same thing with the showing that the converse and the inverse are logically equivalent. So the proof. So you could, again, in terms of test questions, it could be say, prove that, and we give this symbolically. Or another way we could say that is, again, prove the converse and inverse are logically equivalent. So then the proof would be something like, we have to state our assumption. So given the implication, so we have P implies Q. Then we need to show that. So what I'm doing is I'm said in English I've got a converse and inverse are logically equivalent. So I need to specify my implication. We need to show that the converse, so the converse in symbols would be the reverse direction. So Q implies P is logically equivalent to the inverse, which is not P implies not Q. And so again, we just do the truth table. So be careful with this one. This is Q implies P, so we have to do the implication from this column going to P. So I stepped in poison ivy, I got a rash, this is true. I didn't step in poison ivy, but I got a rash, this is true. I stepped in poison ivy and and I didn't get a rash, this is not possible. And then I didn't step in poison ivy and I didn't get a rash, this is true. Flipping P, flipping Q, and doing the implication. So this is true, this is true, this is false, and this is true. What I see then is, so again, making sure here's this left side, or my left proposition here. So, same truth tables. Therefore, Q implies P is logically equivalent to, sorry, the converse is logically equivalent to the inverse. That's required. That was what we're required to find. Okay. And let's see. I didn't show you one where it's not the same truth table. So let's do something like this one, showing that it's not logically equivalent. So here's just an example. So what this is really saying is that the implication is not logically equivalent to the inverse. So that's the inverse right there. So same thing again. We can just P, so we'll do the P implies Q. And then I'll do so that gives me the table for the left-hand side. The right-hand side, I have not P, not Q, not P implies not Q. So again, just enumerating the possibilities for the prime propositions. There's my truth table for the implication, flipping the values for P, flipping the values for Q, and then doing the implication on this column and this column. Make sure I check. There's my truth table for this, for the right hand or for the left hand side, and here's the truth table for the right hand side. Okay, and I was like, oh, did I get the same truth table? And I was like, nope. So here's this. So what I can show you right here. So it's this one. These aren't the same. And right here is not the same. Making sure in the chat that I picked, I'm doing everything all correctly. They are not the same. Truth table. So P implies Q is not logically equivalent. To not P implies not Q. So in the remaining couple of minutes, we can do one more example. So this one is show that P, if and only if Q, is logically equivalent to not P and not Q, or sorry, P and not Q, or Q or not P. Okay. So there's my left-hand side done there. And the next one I'll need to do is, let's do this one and this one. So we'll do not Q. So then it'll be P and not Q. Then we'll need a not P. So we'll get Q or not P. Then I'm running out of space. I'm just going to call that R. Here's R, and I'll have not R here. Just because I'm running out of room there. So are we going to be able to do this in 2 minutes? Okay. So again, that was what we had learned at the beginning of the lecture. We just need to flip the values here. Now we need to use this column and this column to do the AND. We need to flip the values of this one right here. Doing the P, the not P or Q, so using this one right here. So this is true, this is false, true, and true. And now what R is I need to use this column and do the OR operation. So this is true, there's true, true. Uh-oh. So, did I do this correctly? Okay. Well, what we'll have to do is we'll have to return to this for the next lecture, okay? Which will be a good review. All right, everyone, thank you for tuning in for our lecture number 5. And our next lecture will be on Thursday. I have the same. Okay. No lecture Friday. Just double check. Oh, sorry. Yes, it's the Friday. So I think because of the obstacle course. Okay, I think that's right. So I don't think that there is. Next lecture should be next Tuesday. Okay, yep. So just before we go, just make sure that we write is. So is this logically equivalent? And we'll take this up on our next lecture. Okay, next Tuesday. If you have any questions, feel free to send me an email at my RMC account. And the assignment 1 is posted on Moodle, so make sure you have a look at that. Okay, everyone. Thank you, everyone, and have a great day.